Hello, and welcome to this presentation, Understanding Phase Noise, the Cross-Correlation Method. This short presentation will give you a technical, non-mathematical overview of how cross-correlation is used to improve the accuracy and sensitivity of phase noise measurements. This presentation assumes a basic knowledge of phase noise and phase noise measurements. If you're unfamiliar with phase noise, or if you'd like a brief refresher, you might want to watch the presentation Understanding Phase Noise Fundamentals before beginning this presentation. There are many different methods for measuring phase noise. Some of the more common ones are the spectrum analyzer, PLL, phase detector, and digital phase demodulator methods, and each of these methods have different strengths and weaknesses. However, they all share a common limitation in that phase noise from the instrument is added to the phase noise from the device under test. Most of this added noise comes from the instrument's local or reference oscillator. This is a problem because we can't always be sure that we're measuring the DUT's phase noise or the instrument's phase noise. The traditional way of dealing with this issue is to use an instrument that has better phase noise performance than the DUT, with better usually being defined as at least 10 dB or more. However, this approach still may not be sufficient when measuring modern DUTs with very low levels of phase noise. Let's look at this graphically. Our device under test has a certain amount of phase noise that we'd like to measure. Within our instrument, this signal is processed using one of the different phase noise measurement methods. Regardless of the method used, this processing requires a local or reference oscillator. This oscillator has its own phase noise, which is combined with the DUT phase noise. Depending on the relative levels of the phase noise in the DUT and reference oscillator, the resulting phase noise measurement result may not be an accurate measurement of the DUT phase noise. So how do we avoid this problem? As mentioned earlier, the traditional solution to this problem is using an instrument with both low phase noise and a modern phase noise measurement method, such as the digital phase demodulation technique. And although both of these can greatly improve phase noise results, they still may not be sufficient for measuring very quiet oscillators. In these cases, it would be helpful if we could somehow remove, or at least reduce, the influence of instrument phase noise. This would increase sensitivity, that is, allow measurement of very low levels of phase noise, and it would also improve accuracy at all levels of phase noise. Since the 1990s, cross-correlation has been the primary method for reducing or removing the effects of instrument phase noise. It might be good to pause for a brief non-mathematical explanation of cross-correlation. Cross-correlation is a measure of the similarity between two different series or signals, and can also provide the time delay needed for maximum similarity. Cross-correlation is very widely used in many different signal processing applications, such as radar, direction finding, etc. Because cross-correlation identifies what's the same about two signals, it can also be used to reduce or remove the differences between sets of data. In other words, cross-correlation can be used to separate data into correlated or similar parts and uncorrelated or dissimilar parts. Cross-correlation can be performed as an iterative or repeated process. Performing repeated cross-correlations more clearly separates the correlated and uncorrelated parts of our data. Because cross-correlation involves measuring the similarity of two different signals, we implement it by adding a second measurement path to our instrument. The signal from the device under test is split and processed by these two, nominally identical paths. Because the DUT signal is simply being split, the DUT phase noise remains the same or correlated on each path. However, each path uses its own independent local oscillator for measuring phase noise, meaning that the phase noise introduced by these local oscillators is uncorrelated, that is, it's different on each path. Therefore, the measurement results from each path are a combination of the correlated DUT noise and the uncorrelated local oscillator phase noise. When these two paths are fed into a cross-correlation function, the uncorrelated instrument noise is removed or reduced, leaving only the correlated phase noise of the DUT. Let's go over this again graphically. The signal from the DUT is split into two identical paths for processing. Each of these measurement paths uses an independent local oscillator, so the phase noise added by these oscillators will be uncorrelated or different in each path. The output of these two measurement paths are a mixture of correlated DUT phase noise and uncorrelated instrument noise. These are then fed into a cross-correlation function, which reduces or removes the uncorrelated instrument noise. The results are therefore a more accurate and more sensitive measurement of the actual phase noise of the DUT. We mentioned earlier that cross-correlation can be performed iteratively or repeatedly. If we increase the number of correlations, n, this will reduce the level of non-coherent instrument noise in our results. This in turn provides increased sensitivity or a lower noise floor, allowing accurate measurements of even very low levels of phase noise. This improvement is logarithmic. Every time we increase the number of correlations by an order of magnitude, sensitivity increases by 5 dB. For example, 10,000 correlations will lead to a 20 dB improvement. As you might imagine, increasing the number of correlations will also increase the total time required, but the benefits of cross-correlation normally far outweigh the relatively minor increase in measurement time. Typically, the number of correlations used in phase noise measurements are somewhere in the range of several thousand to 1 million. But how many cross-correlations are enough? Our correlation count should be high enough to lower the instrument noise floor below the level of DUT phase noise, ideally with some margin to spare. This helps ensure that only the DUT phase noise is being measured. In addition to the measured phase noise, some phase noise analyzers can also display the so-called cross-correlation gain, which can be used to visually verify that sufficient measurement margin exists. For example, here the gray area beneath the phase noise trace shows the cross-correlation gain. The higher the trace lies above this region, the more accurately we can measure the DUT phase noise. If the trace is too close to or touches this region, we could configure the instrument to perform a higher number of cross-correlations to further lower the measurement floor. In this example, increasing the number of correlations from 100 to 10,000 improves our measurement margin, particularly for phase noise at close-in offsets. Let's end with a brief summary. All phase noise measurement instruments add their own phase noise to the DUT signal. This reduces both the sensitivity and the accuracy of phase noise measurements, particularly for very quiet or low phase noise devices. The traditional solution to this problem is to use an instrument with better phase noise performance than the DUT, as well as a modern measurement technique such as digital phase demodulation. In cases where this is insufficient, cross-correlation can be used to further improve the measurement results. In cross-correlation, a second measurement path with an independent local oscillator is used. The signal from the DUT is split into both paths, each with correlated DUT noise but uncorrelated instrument noise. Cross-correlation is then used on the output of these two paths to remove the uncorrelated instrument noise. Increasing the number of correlations improves our measurement results, often by 20 dB or more, with only a minimal impact on measurement time. This concludes our presentation, Understanding Phase Noise, the Cross-Correlation Method. Thanks for watching.